Hope you guys got a good chance to talk with all the great technology providers here today. As we mentioned, the morning session was more about getting introduced to the technologies that you're going to hear more about in this afternoon session, and get more of an understanding of the kind of the higher level capabilities that these individual technologies can offer you. But now in this afternoon session, we're going to take a look to see how we can use all of these different technologies in a digital thread workflow for automated CNC programming. We're going to take a look at Siemens NX CAM. We're going to go into ThirdWave Production Module. We're going to bring that back into NX CAM and then bring that in that program into Run My Virtual Machine for the verification before we actually cut the part on the machine. So we're going to go through some details and the functions available within NX to teach it manufacturing strategies. We have two example parts that we did this on. The first part is a prismatic part. It has a number of different manufactured features on it that are common in a 2.5 or 3-axis machining, and it's a really good part to be able to show how we can use all of the different functions in NX, so we can teach it how to automatically select the right strategy to apply to a particular feature given the geometry, the material type, and the tolerance that that particular feature has to be made to. So this is where the PMI really gets consumed. In software lingo, I use the word consumed a lot. In software lingo, consume means when you're fully using a data type, right? When you're taking full advantage of it. So again, our test and the development was done with our friends at TRAK. Specifically, we have, to my left, to your right, a VMC10si. It has these specs, the table size. You can see the travel, quite a large, volume within the machine. You can get it with 41.5 or 20 horsepower options. It has a Sinumerik 1 CNC. By Siemens. That's a digital native control, and the Run My Virtual Machine that I'm going to show you works directly with the Sinumerik 1. So we have a digital copy of that exact controller logic. Anything we put through Run My Virtual Machine is exactly what's going to happen on the control. So we'll talk more about that. It in this case has a 24 station tool magazine. It has a 12,000 RPM spindle. And it also has the coolant through spindle option. So in Siemens CAM, we have 4 different functions that are available to us to teach it manufacturing strategies. The first one is called CAM Setup Template. So you're going to have your particular machines and your particular setups, along with the whatever tools you have in your machines. We can set up a template that you can load up every time when you're producing a part on that particular machine, but the template can actually hold operations. So it can hold a roughing operation, a semi-finishing operation, even down to a finishing operation if you choose to encode it within the template. And I'll show you step by step how we do that. It's quite simple actually in NX. Their interface to it is very intuitive. And then we'll go into feature-based machining. So an instance where you have, you open up a part, you enter the manufacturing workspace in NX, and you load up your template file. And in your template file, you have some operations there that you can regenerate, and it'll apply the tool pathing appropriately to the geometry of the part. But you're not going to be able to hit every single feature on the part. That's where feature-based machining comes in. You open up that function and you allow it to recognize manufacturable features. And Siemens NX CAM comes with a machining knowledge database, and it will apply rules that come with it out of the box. You can also modify those rules to your likings and save that out. But those are very applicable to prismatic shapes. And I'll show you how, if even after feature-based machining, it doesn't recognize some features, how you can teach it custom features, and then how you can teach it custom operation sets. So the operation sets would be the exact strategy. So for example, if you have a tight tolerance hole, you might want to produce that using a different strategy than if you had a loose tolerance hole. So we're going to go through that step by step and in detail. So what I did was, I was originally going to do this live in person, but to keep myself within time, I'm going to talk over video recordings that I did. So please do, if you have specific questions, we're going to do another question and answer session at the end. Write down your questions and I will answer them at the end, along with our tech partners. So this first video that I want to show you is the CAM automation, right? It's the setup template. So what I'm doing here is I have opened up an NX file with model-based definition. Those are the call-outs and the requirements that you see there. And I have already developed a manufacturing process to produce, the features there. And what that entailed was loading up my machine, loading up my tools, and then coming up with a roughing operation, a rest machining operation, and then a semi-finishing operation. And I just left it at that. What you're seeing now is me pulling in the machine. And actually, I just set up the part roughly where it's going to be located on the machine there. So right now it's just going through and changing out all my tools to put them in the appropriate pockets on the machine. And there you can just see that I roughly set up my part where it's actually going to be in the vise on my machine itself. So now what I'm going to do is, you can see the operations there in the tree, and you can also see the tools that are assigned within the appropriate tool pockets on the machine there. I'm going to go through and actually just shift select everything, go to object, template settings, and then I'm going to just check on to use what I selected to be put into my template file. And I'm going to do that for my operations as well. So you can see there, very simple interface, choose what you want, right click, and save it within your template file. So now I've chosen all the operations that I want included in that template file, and I'm just going to rename this file as my template. What I'm going to do next is I'm going to open up just the CAD model of this part. So it's just a CAD model with the PMI. So we're right now in the modeling environment. I'm going to switch over to the manufacturing environment. And in this case, I'm going to actually select, instead of one of the existing template files that Siemens comes with, I'm going to choose to browse for that template file that I just saved out. And when it loads in, it actually loads in all my tools. And it loads in my operations that I had set but are not generated at this point. So what I can do now is just go through and make sure that it automatically selected my part. It automatically set up my blank as I had set up in the template file to just be a bounding rectangular block. And I'm just double checking to make sure that it automatically set up my machine coordinate system. So that's a time savings right there. I don't have to go in and do anything. And at this point, I'm just showing that all of the parameters that I had saved for each one of the operations are encoded. It's saved as I'm opening up this template file. So I don't have to go in and mess with my feeds and speeds, my radial and axial depths of cut. It just loads right in with my template file. And I can choose, I could have chose to save this template file for aluminum parts. I could do another one for, you know, steel or for Inconels or for other types of materials so that I can encode my feeds and speeds. But there's other ways to do that in one template file as well with operation sets, which I'll show later. So what I'm doing here is that all I did was I had it regenerate the paths that were already saved as part of my template file. And I'm just verifying that it appropriately applied those to the geometry that I pulled in. I could pull in any geometry, load up my template file, and just regenerate, and it'll pretty much produce almost, you know, the majority of my part. It'll do the roughing operation, get rid of the bulk of the material, do the rest machining with the appropriate tool that I had specified to do the rest machining with. And then I'm left with a circumstance where I have maybe 70 to 80% of my part machined. So the second step now is how do we machine the remaining number of features that weren't machined as part of my template file. So for example, as part of my template file, I had a roughing operation that called out a 1-inch flat end mill. Right. Then my rest machining operation calls out a 1/2-inch flat end mill. And then I think I have another operation in there that calls out a 1/4-inch flat end mill. If I have a part that has smaller features than that, obviously my operations aren't going to fully, you know, machine down to what I was able to machine this to. So there's going to be features left over that need to be machined. And this is where feature-based machining comes in. So all of the rest of the features that weren't machined as part of my template file, I can allow NX CAM to recognize machinable features, those that have not been cut. And then I'm, in this particular demonstration, I'm choosing to let NX apply the appropriate strategy that comes with NX out of the box. So I'm not modifying anything. I'm just exercising the out-of-the-box feature-based machining capability. So in order to do this, what I do is I go over to my operation navigator here, the tab. I right-click and I click on Find Features. Now this gives me access into the machining knowledge database, and I'm able to tell NX what types of features I wanted to recognize. So here I'm going after parametric features, geometric shaped features. And I'm going to turn off recognition of surfaces, any types of operations that will require turning, and any types of operations that might require wire EDM. So I'm just interested in this case on having NX out of the prismatic feature recognition, recognize holes and steps. So you can see there in red, I executed that function and it's recognized all the holes and the chamfers that are required to be made there, and it's picked up on the PMI that's associated with those features, which is what I'm showing here now. So we have the individual features, and then underneath, nested as part of the child of that feature, are all of the PMI associated with it. Later, we can use that PMI to then be more specific about feeds and speeds and strategies that we want to use to produce that particular feature. But all I'm doing now is grouping the features. So I did a right click on the features I wanted to group. And now that it's grouped the features, I'm right clicking on those features that I wanted to produce an operation for. And I'm choosing the types of operation I'm going to allow NX to produce. So in this case, we're using a mill drill, and I've just chosen all of the features under mill drill for it to produce. And here you see that it automatically produced all the spot drilling operations for me. All I have to do now is generate the toolpath and verify that it that it actually correctly produces all of my features without any collisions. So here we're going to verify. Again, I'm starting from the beginning, so it's going to go through my roughing operation, then rest machining, and then it's going to start doing the spot drilling operations. And again, NX came up with these, automatically using the out-of-the-box feature-based machining and the strategies that are encoded within the machining knowledge database. Notice, though, that I have two features that were not recognized and not produced there at the top. What I'm doing here is a quick verification. This is a deviation of the machine stock to the CAD model. And here I'm just picking off points to see how far off I am. Pretty much the part is machined to, a couple of tenths of thousandths accuracy. And that's really to do with the resolution of the STL that's produced. But those two top spherical indents were not recognized and they were not produced. So here's an opportunity for me to teach NX how to recognize a custom feature. And then once I have it recognize that custom feature, I can also teach it how to produce that feature. So in the next demonstration, we're going to go into seeing how we can actually teach the features. I know that these videos are going a bit fast. I hope if you have questions, I can certainly go through and we can go through the steps again during the question and answer session. But if you do have questions, please do note them down. So here in this demonstration, because NX didn't recognize those two top features there, where I have showing at the moment that I have a lot of positive material, I'm gonna go back into my operation navigator, and I'm gonna right click and say teach features. And in this case, I'm choosing to go, and there's a feature type called customer feature. These are any custom features that you teach NX. And I'm creating a recognition rule called sphere cut. And what I'm doing is I'm selecting, let me actually pause it here. So what I'm doing here is I've put the recognition rule under customer feature, and then I've chosen to allow NX to recognize a couple of options associated with that particular geometry. So you can see that I have PMI annotations checked on almost to the bottom of that dialog there. If you don't have that checked on, it's fine. It'll just recognize the shape, right? And it'll try and recognize similar shapes on your part. But because I want to be able to actually leverage the PMI that's associated with that shape to guide the strategy, if it's a tighter tolerance, I'm going to choose to use a different operation to produce it. And you're going to see exactly what I do in order to change that when I do the custom operation sets. But for now, I'm just going to have it recognize the PMI associated with the geometry so that when it does go and recognize a spherical indent, if it does not have a PMI associated with it, it will not recognize that geometry. So you need to have, obviously the geometry has to be the same shape. It doesn't have to be the same dimension. I can have a larger spherical indent or a smaller spherical indent. But as long as, in this case, I have a diameter and I have a surface finish call out, as long as any spherical feature that has those two PMI associated with it, NX will recognize that as my sphere cut custom feature. So now what I'm going to do is I've gone ahead and I right-clicked inside my operation navigator there on the left, that tree. And instead of going to teach feature, I went to recognize feature. And what you see now is when I expand the features to recognize, I have my customer feature, and under my customer feature, I now have that custom sphere cut feature that I just taught it. Any number of features I teach NX will show up under that customer feature option there. So I've chosen for NX to only recognize the customer feature, not the parametric features that we chose for NX to recognize in the previous feature-based machining demonstration. We've already cut those features. There's no need to do that. So now I'm just going to click on recognize features, and you can see I taught it on that one spherical indent on the left. It recognized both of them. And you can see that it also picked up the PMI. As I expand the parent, you can see the child associated with the parent is the PMI. And now what I can do is go through my normal route of right-clicking, grouping features, and then you'll see when I go back into my operation navigator that I now have a feature group sphere cut. And now I want to create an operation associated with that feature group. And I'm going to choose to do a contour mill operation. I'm going to choose to use a ball end mill, but in this case, I didn't see an appropriate ball end mill to choose from. So I'm going to go ahead and pull a ball end mill from my library. I think I chose to go with a 3/16 just because of the diameter of that particular sphere indent. And I'm going to add it to my tool magazine. So again, just pulling a tool out of the library, going back, right-clicking, and creating an operation set, contour mill. This time I'm going to choose my tool. And it's going to bring up the dialog and all the options I have available to set up my strategy to produce that part. So now I'm going to select the surface that that particular toolpath is going to be associated with. And I'm just going to set my parameters. So I'm going to go with a spiral cut. It's going to be climb milling. I like to choose to go with a 10,000 step over in this case, and you'll see how we're going to teach a custom operation set to change that step over based off of the surface finish callout, which will change the cusp height that's left over from the ball end mill. But I'm just checking my feeds and speeds now. Just going off of a book that I had. And I'm going to choose to roll the tool over the edge so we get a clean edge at the top. So I've set my parameters, I generated the tool path, and I'm pretty happy with the result. That looks good. So now I'm just going to quickly verify to make sure that it looks good. So that looked good. And I'm going to exit out of the dialog. Now I have an area mill associated with my feature group. And what I can do now is, let me just go back here, sorry. What I did was I right-clicked on the feature group. And I went to teach operation sets. So because I have a operation associated, right, with that custom feature group, and that feature group holds my custom geometry, right, the custom feature that I taught it, the operations are associated with that feature group. So anytime I recognize features, it will and I want to apply an operation set to that feature, it will automatically group all the similar features together in a feature group and then associate the area mill operation with all the parameters that I just went through and set up with that particular feature. So when I click on teach operation sets, it brings up my dialog, and that really is my interface to the machining knowledge editor. And I'll talk more about this when we talk about the operation sets. But in this particular case, all I want to do is I want to teach NX that for this group, for the feature group sphere cut, I want it to always generate the area mill operation that I just set up. So all I'm going to do is open up the dialog, And then down at the bottom right of that dialog, I'm clicking a button called Teach Machining Rules. That's all I'm doing. I'm not doing anything else in this dialog at this point. Now that I have that, what I can do is I can show you in the machining knowledge database that I have an area mill with all of the parameters just by clicking that button now encoded within the knowledge database. We'll see later how we can apply rules to this, how it chooses the step over distance based off of the call out that's associated with it. But right now, all I want to do is delete the particular features. Sorry, the feature group. And I'm just going to go back to the sphere cut feature itself. And I'm going to have NX generate the operation for those features. So you can see now here, I have that available through my operation sets. And now it's automatically generated that area mill. And all I have to do is generate the tool path. And you'll see that it's going to generate it for both of the sphere cuts at this point. I'm just going to analyze this to see what it looks like. So in this video demonstration, again, just to recap, what we're doing is in the first demonstration with the CAM setup template, we saved out roughing operation, rest milling operation, our tool set, the machine itself in our CAM setup template, and then we open up the part. We went into the manufacturing workspace in NX. And on entering the manufacturing workspace, it asks you what template do you want to use. So normally you would just choose one of the out-of-the-box templates, like if you're doing just a basic milling operation, a turning operation, a contour operation, whatever. You can use those templates. But in this case, because we saved a custom template, I browsed for where I saved that custom template, opened it up, and on loading the workspace, I already had my part. NX recognized the part that I'm going to cut. Because in this case, I only have one solid body, it automatically selected it. Otherwise, you would just have to double click on it and select the body that you want to produce. And then once you do that, it should auto generate the stock, the blank. And only because the blank that I chose to generate was just a rectangular box. And then the MCS is automatically, centered at the top because that's how I saved the template out. And then I just have to regenerate the operations and verify. Here we taught it to recognize custom features that the feature-based machining didn't recognize. And all we did for now was to say that if you see a spherical indent, cut it with an area mill operation with these particular parameters that I had set up. Again, that step over of 1/10,000ths, and the depth of cut and everything that I had set up there with the feeds and speeds as well. But right now, it doesn't know, if I have a surface finish call out on one of them for an RA value of 3.2 and the other one at 25, it's going to use the same operation set. It doesn't know right now how to distinguish between the two because we haven't set up the rule yet for it to what to do with the PMI. It's reading the PMI, but it doesn't know what to do with it yet. So this next demonstration that I'm going to show you is how we teach NX to use the PMI and to apply the appropriate strategy based off of that PMI. I have two different PMIs associated with this. One is the diameter. The other one is a surface finish call out. I'm going to show you in both cases how we can teach NX to use either or. So here we're going to go into the teach operation sets. Right there in the screen, you can see the diameter call out here. This one has a plus minus 5/10,000ths requirement. This one has a plus minus 1,000ths requirement. So right now we're going to teach it a custom rule to read just the diameter call out and make a decision on the radial step over based off of the diameter call out. So what I'm going to do now is I'm going to go into my modeling workspace. The reason I'm going into my modeling workspace is normally when I put on PMI, so you see there's a tab at the top called PMI. If I click on that, I have a number of, obviously a different, I can add GD&T to this, I can add dimensions, I can add different callouts. But when you add a diameter callout, what you get is that dialog that pops up there. What I want to make sure is that I type in diameter. So that's the reason I'm bringing this up. That's the key to be able to consuming that diameter, because we're going to call that name in the operation set. So I already had it in there before starting the video, but I'm just showing that you want to make sure that you call it something. It doesn't matter what you call it. Call it something that you would recognize when you're creating your operation set. Okay, and now with the surface finish call out, you can see that if you were to put on the surface finish call out and you wanted to put a roughness measurement, the A value here, you would choose either something in the list or type it in. But typically the way that this call out works is you have to put RA space the value. As it stands, that's not consumable. The way that we make it and force it to be consumable is that we get rid of the RA value. There's ways around this, but basically this is not a integer or a what NX calls a real value, like a double precision value. It ends up being a text value when you have the RA in front of it. If you delete the RA, it's easier to parse that number in our operation set code when I get to that point. So all I'm showing here is that if I was to select an RA number, it automatically appends the RA there. All I'm going to do is delete it so that I just have the numerical value. So back into my manufacturing environment. And what we're going to do is we're going to go back into that feature group for the sphere indent. So I'm back into my machining feature navigator, and I'm going to right click on my sphere cut because I made that change in the modeling. It asked me to update it. I'm going to go to my feature group. Right click, insert, operate. Oh, sorry. So I'm just recreating that operation. So what I did there, I kind of skipped over it. What I did there was, and when the screen went blank, I already showed you how I created the area mill operation, right, in the previous video. In this case, because I have two different requirements for the two features, I'm creating two different area mill operations. One is for the looser tolerance, so you can see that I don't have quite a tight helix, right? It's a little bit more spaced out. So I chose to create that, and you're going to see that I'm going to associate that with the looser tolerance requirement, and I'm going to recreate the area mill operation that I created in the previous video and associate that with the tighter tolerance condition. So what I'm going to do is simply just right click, paste the feature group, and I'm going to rename this particular feature group, the first one, to say rough. Same thing for the milling operation. And I'm going to rename the second one to be standard. I'm going to associate the right geometry with my feature group, and I'm just going to double click on the area mill parameters, and then I'm going to adjust my operation parameters. So I'm going to choose the step over distance of from 40 thousandths to 10,000. That way it generates with a tighter helix. I can choose to change any one of those parameters. The idea here is that I'm creating two different operations and associating them with the two different tolerance requirements. So now what I'm going to do in the previous, when we were doing just the operation sets and associating the operation to the custom feature, all we were doing was clicking on the teach operation set. So we're associating the milling operation to the feature group. Now we're going to go in and actually access the attributes of the geometry, which is the PMI. And you can see here that when I actually click on my feature group, I have accessible now the PMI. So I've got my diameter call out there. That would not be accessible to me had I not put in the diameter keyword in the PMI. So that's key. If you were to come in the custom up, you wouldn't see that there. It wouldn't be accessible. So that's why it was important to go through that. But now you're going to see how anytime I click on one of my parameters that are associated with the feature group, it will append the command here. And I have all my different options to actually create an equation that will guide NX to do, to change a certain parameter, whatever way I want, based off of whatever I choose it to change it off of. And in this case, it's going to be the PMI. So what I'm going to do is, because I have a diameter plus and minus, I'm going to say, okay, let's take the upper tolerance requirement, and we're going to add it to the negative of the lower. So we're getting the span of the tolerance. Plus or minus 5 thousandths means that I have a span of 10,000. So all this equation right now is saying is if the span is greater than, I think I put in 8 thousandths there. Yeah. If the span is greater than 8 thousandths, choose to use this area mill rough operation. And I'm gonna click down there and say teach operation set. And all I'm gonna do now is I'm gonna just come and copy that, because I'm gonna paste it for the area mill operation here. So I'm gonna go into that feature group, object, teach operation set, click on my sphere, cut again, paste that. But this time I'm gonna say if the span of the tolerance is less than or equal to 8 thousandths, use this area mill, the parameters that I had set for that area mill. So essentially, I'm creating an area mill rough and area mill custom operation set. And those are now tied to the PMI, which I'm going to show here. I'm going to pause this for a second, which I'm going to show here in a minute to the, to the span of the tolerance requirement. So I came into my machining knowledge editor, and I'm just showing you that now I have two different area mill operations associated with my sphere cut geometry. And there's my equation there associated with the actual operation itself. Now what I'm going to do is delete my feature groups, and I'm going to go over to my machining feature navigator. I'm going to right click. Sorry, this is happening kind of fast. I'm going to right click on my recognized custom feature. And then I'm going to go, I'm going to go directly to create operation set. Create feature process. So on the previous tab, the operation navigator, I deleted the feature group rough and the feature group for the spherical cut. And I'm going to have NX now automatically recognize the features, group them, recognize the PMI, and then associate the appropriate area cut mill operation according to the tolerance requirement. So it's going to do that very quickly. I'm just going to click the button. And this time in my operation sets, you can see I have accessible those two new rules. So I'm going to want to check them on. And now NX is going through and actually creating the area mill operations for those particular features. So you can see there, it's re-added those in. And all I have to do now is generate, and we can take a look to see if it associated it with the right geometry. So there you can see with the looser tolerance requirement, we generated the rough area mill operation. And for the tighter tolerance, we generated it for the tighter tolerance condition. I think what I'm going to do next is I'm going to delete these. And then I believe I go back into my modeling, and I'm going to swap these around just to show you that it correctly generates the program. So I'm going to change my 5,000ths requirement for the sphere cut on the left to 2,000ths. And I'm going to change my 1,000ths to something looser, 6,000ths. So because I had my span as less than or equal to 8,000ths or greater than 8,000ths, now one will fall under one requirement, the other one will fall under the other requirement. So what I'm going to do now is accept the changes that I just made to the PMI, and then I'm going to shift select both features and create feature process. So remember, previously, this was the looser tolerance, this was the tighter tolerance. So it generated the appropriate program. The test here is that now that I change the PMI, will it automatically associate or swap the operations because my tolerance has changed it around? So there, now you can see already just by the highlight that it's appropriately applied that logic. And I'm gonna now just generate the toolpath to visualize it. So you can see there now the tighter helix is associated with the tighter tolerance requirement, and the looser helix is associated with the looser tolerance requirement. So in this demonstration, I chose to use the diameter tolerance, but practically the spacing or the between the step over is more appropriately associated with the surface finish call out. So because the surface finish call out is a text value, I thought that it'd be a good demo to show you how I deal with the text values, because that seems to be a little bit more tricky. In this case, I can directly select, the and get the values, the numeric values for my tolerance in my operation set dialog. But if you want to get the surface roughness, it's a little bit, you have to add a step in there. So I'm going to demonstrate that next. So again, another example of the operation set. So in this case, we're going to now focus on the surface finish call out. The first spherical indent has a surface finish requirement of 3.2, and the second one has a surface finish call out or requirement of 25. Again, I deleted the RA that preceded the number. So I'm going to go into my teach operation sets, and I'm going to delete the existing condition that I taught it in the previous demonstration. And now I'm going to access the surface finish parameter. And you can see that I have a lot of different, let me just pause that there. So going back, what you notice here is for my surface finish, my 3.2 is in quotes. That's indicating that it's a string value. In order for me to use math functions on it, like greater than, less than, whatever I want, I need to convert that string value to a real number. So what I'm gonna do is I'm gonna click on my FX button there all the way to the right, and that's gonna bring up a bunch of functions that are built into this operation set dialog. And I'm gonna choose to use a function called toReal, and that'll just convert any string value that's within the parentheses of that toReal function to a real number, and then I can do the math on it. So that's the only extra step that you need to take. It's just a demonstration of, what's built into the teaching operation sets in NX. So again, I'm going to click on the functions. I'm going to go down and find the appropriate function there, and there it is, toReal. And you can see that it appended that there. Now I'm going to click on the surface finish. It's going to put that in my equation. I'm going to end the parentheses, and then I'm going to set up my condition. So in this case, if it's less than or equal to, so if my surface finish value is less than or equal to, I think I put in 5. So if it's an RA value of 5 or less, it will choose to use the area mill operation and all the parameters associated with it. So I'm going to click on teach operation set and then OK. And I'm going to do the same thing here. I'm going to go into my sphere cut rough area mill. First, I'm going to delete the existing condition. You can have multiple conditions in there. Yeah, obviously, there's going to be other conditions you want to put in there. For example, you probably want to tie the dimension of the particular feature to the size selection of the tool that you're going to use. So I went in and chose to use a 3/16 tool because I saw what the diameter of that feature was. But I can actually put a rule in there and say that, choose a tool that's 75%, 50%, 25% of the size of the feature dimension. So that can be one of the rules that's within your rule set in the operation sets dialog. So what I did there was I just I deleted the previous rules, and I created new rules for the surface finish, and now I'm generating the operation so that you can see how it's now tied to the surface finish rather than the diameter callout. So there, when we actually visualize it, you can see that for the smoother surface finish requirement, you have a smaller step over in the helix. If you have a rougher surface finish requirement, the helix step over is now greater. What I'm doing now is I'm gonna do the same thing. I'm gonna swap around the surface finish requirement and have it regenerate the path to see if it appropriately, took the equation. This is just me debugging to make sure that the logic I put in there is correctly put in and that it actually applies the right strategy. So again, I've swapped around the surface finish requirement, and I'm gonna go back into my application, manufacturing, and then we're going to accept the changes because it recognized that something changed about that geometry. In this case, it was the PMI. I'm going to right click and create feature process. And now you can see that it's generated the appropriate feature process. We're going to generate the toolpath so we can visualize the actual helix path. And you can see that it's appropriately applied the right operation, the right parameter of the area mill operation to the right feature that has the surface finish callout. So I'm going to go in and actually verify the toolpath and visualize the deviation so you can actually see this a little bit better. So you can see there that my feature on the left is going to have a rougher surface. The feature on the right is smoother. So again, this is this is a way to capture best practices. Your experienced machinists have years and years, probably decades of experience in machining, using different tools for different types of materials, cutting on different machines. There's just so many variables that go into what's the strategy I apply to machine a particular feature. What I'm showing you is the ability for you to capture that knowledge in a database, so that if your experienced CNC programmer is filling up your machining knowledge database, you can have a novice CNC programmer come in and open up a part. So long it has the PMI on there, just select the appropriate operation set or the custom features that you want it to recognize. You saw that in the list. I can check on and off. So you can have a separate database for aluminum parts. You can have a separate database for different types of tools, like solid carbide or other types of tooling. You can really set it up however you want. So that's the easy way to do it. There's ways in which you can have one database with a bunch of operation rules that you set up. So you can say that if the tool is this material, because NX has that information about the tools, if the material is aluminum, titanium, whatever that you're cutting out of, you can choose to set up an equation within your database that then chooses the appropriate strategy to cut from. So there's multiple, what I'm saying is there's multiple ways that you can set this up according to how you would like to set it up. But obviously the value here is that now I've gone through the 4 main functions that NX gives you to get NX CAM to automatically generate a CNC program based off of the geometry and the PMI that's associated with that geometry. So you can encode best practice strategies to produce that particular feature. So here's the complete MBD workflow. It's a quick video. I'm just opening up the part and I'm going to apply all 4 of those functions that I just talked about. Again, just so you can see generally how quickly this happens from start to end. Obviously, there's a setup time. The setup can take a long time, and you can continue to, it's a living document. You can continue to modify it as you find that, that helix step over didn't produce the surface roughness I was looking for. This one does, edit the machining knowledge editor, save that in so that in the future you use that going forward. So here I just applied my template file. I'm just making sure that everything came in correctly, making sure my MCS was in the right spot. And now I'm going to generate the tool path to see how it handles the geometries of my part. So a word of note here is in each one of the operations, in this case, I associated the operation with a specific tool. So it's using the 1-inch flat end mill for this roughing operation because it's assigned in the operation itself. But I can create an operation set rule that governs the diameter of the tool that it chooses to use based off of the features that are contained within it using the equation editor. So here I'm just double checking, making sure my feeds and speeds are good. All the parameters that I had saved in the machining knowledge came through. And I'm just checking to make sure that the tools that were associated with this particular template also came through. If you choose not to save the tools in the template, you can let NX grab a tool from the existing library, and that's where your equations have to come in. If you don't have an equation set up to choose the appropriate tool, it'll just choose the largest diameter tool to produce that particular feature by default. So here I've opened up my find features and I'm letting it, find holes and slots as I did before. These ship with NX CAM. This is the out-of-the-box feature recognition. I'm going to click on the button. It's going to recognize all the different holes. And then I'm going to group those holes so that we can create operation sets associated with the groupings. Again, it's picked up on the PMI. So there we have two different groups that it created. You can see those two there. And then I'm going to go back and I'm going to right click on those features and just have NX create the operation set automatically. So in this case, for the feature recognition, I didn't set up any rules for how it chooses the tools. I'm letting NX choose the tools by its default behavior. And the default behavior is use the largest tool that you can fit in the feature. So there it's automatically generated the operations, and all I have to do now is generate and verify. So the nice thing about this is that, you know, I opened up my template file, I applied feature-based machining. If I so choose to, I can right-click on those operations and I can say, associate this with my template, right? And then I just go in File, Save, and I choose the template name and just hit Save. So now, if I was to adjust any of my, like for example, my plunge for my, you know, drilling operation, I'm nervous. I hate breaking drills, so I go super slow, and I almost always change the plunge rate. And let's say that for next time I don't want to keep doing that over and over every time it automatically generates. I'm gonna just associate that with my template file. It's a file save, and next time I open it up, that parameter is saved in there. How am I doing on time?
Well, I'm not sure. So we're about an hour in
Okay.
from return from lunch. I know Nick was going to speak shortly.
Yep.
And I know Tyler was going to come up and do a little more demo. So just checking in with you, Nasir.
Okay. Real quick time study. On the left, we're manually programming the part. On the right, we're using the model-based workflow. I'm not going to let this run the whole way. I got the times down here. It took an hour, 25 minutes for the manual workflow. And for the model-based workflow, it took 8 minutes. That 90% time savings. It's 90%. It's not 5%. It's 90%. Most of the time, we see between 50 to 80% time savings. That's generally what we've seen. Obviously, you can see how with all the ways in which NX gives you to teach it, how to come up with the strategies, come up with the operation sets. You know, you can teach it any which way you want. Oop. So the next step here is now we've reduced our programming time by having NX automatically program the part. Now I can put this through optimization to reduce the cycle time. So this is a quick video to show that. We're going to take our program. I'm just going to skip through it here because I'm just re-verifying that the program runs correctly. And then what I'm going to choose to do is use the ThirdWave plugin. You can see it there at the top left. I'm just clicking on the ThirdWave plugin. It's asking me what operations do you want me to optimize. I'm just selecting the operations I wanted to optimize. There's some other options there. It uses the tools that are in NX. It uses the stock, you know, the in-process workpiece. It takes all that information in as well as the tool path, and it analyzes the tool path. And all I really do is I click on the, like in this case, I chose to bring in two tool path. I'm just clicking on one of them, and I'm letting ThirdWave choose the suggested optimization parameters for me. I'm not making any other changes. So it's just a few mouse clicks. I hit optimize, it optimizes the program, and it'll tell me the potential time savings. In this case, I won't go back. It's gonna, in that same interface, all I did was once it optimized the toolpath, in this case, it did it, I think it was like 22% time savings. I clicked the button to say, okay, import that toolpath back into NX, and then I just post it out. I think one of the things that I went back in to show you here was that I can get a little bit better time savings by adjusting the feed per tooth. But I bring that dialog up to show you that now for every line of code, I have a custom feed rate associated with it. So ThirdWave looked at the force spikes, it minimized those, and it also saved me in cycle time. So here I'm just verifying the posted program is going to work on my machine. This software here is run my virtual machine. So this is the digital twin of the TRAK VMC10si. And I go through this before I put anything on the machine to guarantee that that program's going to run correctly. I've got all my tools in there, tool holders. It's a complete digital twin of my process. So this is just a quick video showing going, now onto the machine and actually machining that part out. I'll skip over this just because it's going to take a bit. Again, these are the different processes involved. 90.58% time savings in programming, 21.5% in cycle time reduction, and then over to run my virtual machine and on the actual machine itself. Again, this was the workflow that we went through. Here are the inspection results. And here is the takeaway, time savings. Traditional method, total time 16 hours, 5 minutes, 58 seconds. This is accounting for the time it takes to produce the program. The cycle time, if I was to run 10 parts, how that cycle time is multiplied across 10 parts. And then this total time is just the time in programming plus the time to actually produce 10 parts, 16 hours. Model-based, I'm down to 14 hours, 48 minutes. That's an 8% time savings. Optimized, I'm down to 26%, or I'm saving 26.8% across just 10 parts. So you can already see the return. Imagine making 100 parts. Right? Softwares pay for themselves immediately. This is a very fast return on investment. Next demonstration is on an airfoil. We're going to go through the same process. There's 4 operations. There's a roughing, rest machining, a semi-finishing, and then a finishing operation. If you want to see it live, we've got it set up here on the TRAK machine tool. We paused it in the middle of the finishing operation so that you can see that happening live. So I'm going to hand it over to Tyler, who's going to talk more about the ThirdWave solution and the optimization that they can go through.
All right, I'm going to back up one slide here real quick just to kind of reiterate what Nasir was talking about, how simple it is to take it from NX into our software. So up on the right corner there, nice plug-in button to open up. And this is real time. I did not speed this up at all. But selecting basically the operations that you want to use, the in-process workpiece, which for this particular one, so there we go. I just reduced the resolution a little bit, but pulled it apart. I'm just looking at how kind of just a small snippet of the part, but it is now loaded. So all of your tools, your workpiece, your tool path is all now brought into production module, and it's just going through the analysis. So I was only doing a small part, just how fast, but that is literally how fast you can get it into the software. And then basically what Nasir was just showing, where we can run the optimization. But I want to show before running the optimization, I like to look at the analysis capability that we have within production module, because I think to me the optimization is the last step. If you bring in a really poor toolpath, you'll get a better poor toolpath out with the optimization. But if you can leverage that iterative cycle where you're bringing it into PM quickly, and you just saw that you could bring it in a few seconds, looking at what you're doing and then going back to CAM and making changes and bringing that in, you can get a significantly better output than just running the optimization alone. During lunch, I did get a question regarding, are we looking at putting any other CAM systems into our plugins? Because as I mentioned, we have 3 of them so far. And the short answer is you can talk to Austin afterwards. But we always have the option to bring G-code in. So no matter what machine, no matter what software you're using, you can post the G-code out and bring it into our software. It just requires an additional setup for the machine kinematics. And you'll have to make your own tool list and bring the part in the current process state that you want. But I wanted to show a little bit of the analysis. So here's just a quick screenshot of all of the variables that we calculate through the entire toolpath. And you can select which ones you want. If you want more, you want less, or if there's specific ones you look at, it'll speed up the analysis time by reducing a few. But some of I have one use case here about kind of one thing that I have found extremely helpful just quickly, and it doesn't even take much to look at, but how easy it is to kind of identify, is your toolpath good? So you can run my virtual machine, you can look at the verifying the toolpath, and it'll tell you if you're going to crash the machine or not. Here it'll tell you if you have a little bit of a point where the tool is kind of coming back in contact, whether it's rapid or just kind of rubbing against the part. You can see that force spike there. And that's exactly what was happening. If I were to zoom in on the bottom here, there's kind of a couple little spikes. And what I was seeing is the tool is wrapping around the workpiece and causing it to engage all of the tool, which is just causing, an increase in force, and now you're going to cause more deflection, which could be problematic down the road, or you're going to be detrimental to the tool at that point. So using some of the features that I showed earlier, or everything that's on the screen here, now is the time that you can look at everything that's going in, how the tool is engaging, what temperature am I at. You want to make sure you're not exceeding that. And maybe it could be that you bring in a recommended tool and you're way underutilizing that tool. Let's fix that now and put a good tool path into the analysis and then move on to the optimization. So moving on to the optimization, we have the capability to look at all of these optimization parameters here: tangential, radial, axial, load per unit length, horsepower, and tangential force per tooth. These are what the optimization algorithm are going to try to hit for every instance in your toolpath. So we're on a sub-revolution computation. And then just to let everyone know, so you're like, all right, well, is it changing my toolpath? What's it doing? The motion is not modified at all. So what the actual kinematics are remain, so you're not doing something, it's not going to do something that's unexpected. It's just modifying the feed rates. And then if you are concerned with, all right, I can have this tangential force, but now I could really still be kind of locally overloading my tool, you can put a limit by. So you can limit, all right, I only want it to go this fast, or I only want this peak chip load. I don't want to, exceed too much. So it gives you a little bit of control. You can control the feed rates and say, okay, I do not want to exceed, my machine's limits on how fast that tool can actually move. And then we've also run into some cases where sometimes you want to make sure that it's not going below an in-cut feed rate. So you're, maybe coming through and you're kind of looking for a level that you want to be at, but it looks like it's just completely slowing down to almost nothing to try to get that. You can push the tool a little bit. You have a little bit of override capability. And then the last item that we have in there is you can look at modal analysis. So you can go out understand what the modal analysis for your tool, your workpiece is, you can bring that in, and production module will attempt to adjust the RPM slightly so that you are able to stay within a stable cutting zone. That does take a little bit of extra effort to get that in, but it's it's a usually I'm sure a lot of you are familiar with tap testing. That seems to be the easiest way to do it, but there's many ways that you can derive that and bring it in, and PM will use it to maintain a stable cut. All right, and the last one I just want to reiterate kind of on what Nasir was going after. He was talking about that 20% cycle time savings. That is what we saw using just the optimization. So all I did was take his toolpath, bring it in, hit optimize. A few seconds later, here's a new toolpath, and we got 20% cycle time savings. I'm convinced if we were to actually iterate a little bit and spend, just a couple iterations back into CAM, this number could be substantially higher. So it's kind of, what you're after. But all the tools are here. Be happy to talk about it a little more this afternoon if you have specific questions. So I'm going to hand it back over to Nasir.
Thank you, Tyler. So what you're looking at in terms of the optimization, right, we're looking at one particular product, production module, where our demo is a blade, and the material is titanium. So if anybody's cut titanium, it's very tricky. With the other products that aren't being mentioned, Distortio and Advantage specifically, choosing the right feeds and speeds, radial depth of axial engagement. Advantage will give you, that's a full FEA package. It'll give you a lot back. So you can choose the right parameters to start off with. And then Distortio can look at, how your machine dynamics. So you can further refine, your machining path. Out of ThirdWave, we bring that optimized program back into NX with a click of a button. We use our post to post it out, and then we load up that program into Run My Virtual Machine before we start cutting on the actual machine. So what I'm showing here is taking that program and now running it on the digital twin of our TRAK VMC10si. So I have in Run My Virtual Machine, it's just like standing at the machine. I have my operate interface, the Sinumerik operate at the top left. That's the exact interface that I see on the machine. On the bottom left, I have the keyboard panel. That's exactly what I see on the machine. So the exact steps that I have to go through to load the program from a USB or from the network, I take the same exact steps. In fact, I have to enable my spindle. I have to enable my drives. I've got to put my feed rates up to 100%. I've got to switch my key over to whatever position I need it to be in, 1, 2, or 3, for the access level. And then I have to hit cycle start. So it's a great, it's almost like muscle memory, just as if I'm standing at the actual physical machine, and I can see exactly how my setup, is going to be once I'm cutting. So in our demo here, we chose not to use a tailstock, right? It's not holding the blade from the tip where you just have it cantilevered off. If we were to use something to hold the tip of the blade, we'd want to make sure that we have the clearances and all that. So this is a great environment to be able to, actually come up with your setup and then simulate it. And then this is just a short video showing that program actually running on the machine. Again, we're going to have a word from a manufacturing company here, a great friend of ours, Neep, talk to us about kind of a real world case and how they're seeing this workflow. But then we're going to have a question and answer session. And again, we're going to have opportunity to network. So we do have the machine here. We have it ready to go. If you'd like to take a look at, the Sinumerik One options, and we can have a more detailed discussion about the machine itself and the capabilities. So the quick chart here, the takeaway. Again, we're getting to 25.6% of time savings using the optimized path. The model-based workflow does give us the shortest programming time because I'm not going through the optimization, but you can see the optimization is only adding like 5 minutes, right? And it depends. I mean, obviously it's not going to be, it's dependent on how many operations you have, how long the operation is, so that time can increase. But if you look at it over a number of parts, and we're just looking at it over producing 10 parts, that extra time in getting that program is well worth it because the time savings you get out of the cycle time magnifies across the number of parts that you're producing. So you get that much more value out of the optimization chain than just going through the model-based workflow alone without the optimization. So the value of the digital thread, obviously we talked about automation of production programming. You can save up to 80% on programming time. You can save up to 50% on machine cycle time. You can capture and encode best practices for consistent programming. All of these are what I'd like you to take away from this presentation. And the value that these software solutions, the TRAK machine tool, the hardware is bringing to you. One of the quick, before I end and call our friend Nick up to talk about his application at his company, I'd like to just say the value of the digital twin. And I know we talked about this. This will be more in depth in a future event. So be on the lookout. We have an events page, ccat.us/events. We'll also send out notices if you choose to know about it, how we can use real-time data to further control our manufacturing process. So the question was that I'm going through simulation, but what happens in actual reality, right? Things change, it's transient. Tools wear out. Things, as you're producing parts, there are certain physics and conditions that are changing. So we want to be able to capture that and see how that's affecting the quality of the part. And if we start to get to a point where we're able to predict the quality of the part's going to decline, what do we do to correct for that? And this is where the digital twin comes in. Here's a quick example. Stock material on the left, we're producing that circular feature at the top. We've got a flat end mill, and that's the resulting geometry at the top that we're producing. Very, very quickly, we produce 18 parts. We're measuring the diameter of part number 3 and part number 12. At part number 3, we're hitting a 1 inch 856 thousandths. By the time we got to part number 12, we're 1 inch 741 thousandths. Diameters decline. It's smaller. Why? Because the tool is wearing out, and so that's affecting the diameter of my of the resulting part. The tool wear obviously here is magnified because we're measuring diameter. But if we had an edge device connected to the machine while we were producing those 18 parts, and the spindle power that was consumed by the spindle to produce part number 3, or to produce the feature on part number 3, was hovering at about 950 watts. When we're producing part number 12 with a dull tool, it's consuming more power. We're up at about 1075 watts. And if we take a look and plot these 2 points, right, over on the right, we have, for a power consumption of 950 watts, we're producing a feature of 1 inch 850 thousandths. For a consumption of 1075 watts, we're producing a feature of 1.75 inches. So if we just do fit a line to it, or calculate a line equation, that's our model. That's our predictive model. So now if we're producing the next part and we're consuming 1,012 watts of power, we can predict that we're going to produce a feature of 1 inch 800 thousandths. This is what we mean by a predictive model. So instead of waiting or stopping the process to take the actual measurement, we can predict what the feature dimension is going to be. But what's important in this case, and we talked about this before, is finding out the cause of the issue. So in this case, we're associating the decline in the diameter to tool wear. But there's other causes, and how do we break up the percentages? Because that's important on what we do to correct for that issue. Do we change the tool radius offset? Do we change the feed rate override? Do we change the spindle speed? You know, what is it that we're changing about the process to mitigate the issue? And this is where the physics modeling comes in extremely handy. You can pinpoint exactly what's happening. You can measure things. You can measure tool wear. It's very hard to measure tool deflection. It's hard to measure workpiece deflection sometimes, depending on your process or conditions. But the physics modeling helps you to decipher what the cause of the problem is. And that goes into the corrective action control. So we'll talk more about the architecture in the future and how we connect all the digital data to a central system that processes this and continuously trains a predictive model. We'll talk about the edge device in more detail, and all the software that comes on the edge device for you to be able to capture signals for specific features. So if I have feature ID number 1, which is diameter of a hole, and feature ID number 2, which is depth of a hole, I have one manufacturing operation, op1, that does a drilling operation to produce that hole. I want to capture and segregate the signal just for that hole, because then I want a segregated signal for my next hole. And that's the way I'm able to take the dimension from the feature ID, associate it with a manufacturing operation number, and eventually to my signal. And those are the two data streams that come in to teach a predictive model using AI, machine learning. I mentioned that I had a screenshot of all the parameters we can get off the edge device. Here it is. We can get, this is showing 75 parameters. We can go, I believe, up to 100 different parameters if we wanted to capture them at a rate of 500 hertz each. In fact, we can go up to 1,000, I believe, if we change some parameter. So this is one thing that we're working on now. I don't know if this video is going to show it. Yep. What this is showing the predicted deviations of a part given the real-time data we get off the machine. So this isn't measuring the part afterwards. This is taking the data stream and predicting the deviations while we're machining the part. So this is the value of the digital thread. But like I said, we're going to hold a future event. This is a teaser. I hope to see you all back for that particular event, because we're going to get down into the details of what goes into setting this up. And you know, we want to package the solution to you like we're showing you today on the digital thread with all the different tech partners. You know, we've worked everything out. We have a working VCP file, the digital twin. We have a working post for the TRAK machine tool. If you are going to move forward and proceed with adopting some of these technologies or the entire package as a whole, you've got a support team here. You've got a lab that has already gone through and gotten this stuff to work. So just know that you have a resource here. We're here for you as your applied R&D lab. At this point, I'm going to ask if Nick can come up and talk to us a little bit about the technologies that he's adopted and how he sees the value.
Thank you, Nasir. All right. I swear I did not put this slide for myself. I'm glad I didn't wear the same shirt. So, all right. So I'm from NEAP, New England Airfoil Products. We're down in Farmington. So we make airfoils. Been here in about 2 years in Connecticut. So I'm not originally from Connecticut, but what I'd like to say is really that Connecticut has such a unique ecosystem to support manufacturing. And we're really grateful for the partner that CCAT has been to us. And when I walked into the organization, we already initiated the work with ThirdWave. So we were already ongoing on a product for GE, actually. So it was an interesting thing to step into. I think when we started that journey, there was a little bit of that hesitation towards something new, something different. How real is this? You know, you see these potential benefits that some of this can bring, and you wonder if that's real. Are you going to really see it? We haven't tested it. I think a few years ago, a lot of you will probably identify with this. We were in a situation where we were actually struggling with the know-how because of people leaving the industry or the company or whatever it is. We were struggling to get the materials, forgings, so on, tooling, so on and so forth. And then there was a spike in the demand that we saw from aerospace manufacturers. Like the OEMs wanted, whether it's a military product or commercial product, they wanted more and more and more. So I think the response of our organization and turning to some of these technologies that we started to explore with CCAT was out of a need to respond to this market environment that we were in at that time. We turned to CCAT really, and it was a great partnership that we created. They helped us to kind of gain some trust into what we were doing. They gave us a playground to do that in. So it was a great facilitator to just gain some confidence. Will this work or will this not work? So now, looking back, I guess the reason I'm here is to talk about like kind of what we saw from actually going down this path. I'm glad we did because a lot of the things that the people before me talked about, and especially now Nasir and brought up some of the savings in times, they're real. This is what we were seeing in our organization on our product. We started with one particular part. It was our kind of like test child of learning about how this works and what we can do. And what we've observed was not just the cycle time, which is very much in line with what Nasir has showed on some of these slides, which probably will get a lot of you excited already. I think Tyler brought a really good point of if you were to even go further and optimize some of the things that you can see it even more. And this is what my engineers right now are actually doing since even last year. So once we got really comfortable, learned it out, it became the new normal for us. We are looking at NPIs with a different set of eyes. We're looking at how we're going to attack the new manufacturing process with that already in mind. But we're also going back and looking at our existing long-term LTA parts that we run, legacy parts, whatever it is. Can we do things better? Can we go back and change the way we were doing things based on what we've learned so far? And the answer is yes. And I'll give you some tangible things. We challenged the engineering organization last year to do what everybody loves, cost savings. I can tell you that for an organization, and we're a medium-sized company, already this year, our budget target was roughly $500,000. They found me 750 already, and they're still not done. So it is a great testimonial of what this can do. We saw it in the savings on the tool consumptions, cycle times, quality. So that was one important thing for us. Even machine, like the fatigue of the machine, like was a factor for us as well. The one maybe thing that nobody actually would think about what it did for us in the time when we were trying to attract new talent, having these new things to play around with actually attracted some really nice new engineering talent to our organization. And that's not easy to do in aerospace alley. Like you're competing with the big names of the aerospace industry. So a young engineer walking out of the college doesn't necessarily consider need to be the high tech. I can play with something really tangible there. And this kind of gave us a little bit of an into that young talent pool. And actually, if we recently did a video for CCAT, about 30-minute long, highlighting some of these things, and the engineer that spoke on it did a roughly 30-minute presentation of taking you through the T's and C's of what we do. What people don't know, he did it in one take. He was so enthusiastic to talk about this that the person that did the video was shocked that he was able to do this all in one take without a mistake, just following through and with such enthusiasm talking about the product. So I think for us, just to bring this back, everything that you've seen today, it's worth it. It is worth looking into. It's worth building a business case around it for your organization, because obviously you need to scale it to the appropriate to really see what benefit you can have, and how in the future. I mean, we just want to start engineering smarter from the get-go, and this enables us to do that. So thank you all for the time.
Thank you, Nick. So at this time, I'd like to invite our tech partners to come back up. Another round of question and answers. And then we'll open it up for, Eileen, is it networking after, or are we doing the closing and then networking? Closing?
Closing.
Okay. So we'll do question and answer. We'll close out. I'm going to talk a little bit about the grants and give you an idea of what the cost is of the package solution and what the state of Connecticut is doing for the manufacturing companies to reduce that cost for you. So right after that, after the question and answer, we'll go into that, and then we'll open it up. Tech partners are here. Please do meet them. And if you think this technology that you're hearing today is appropriate for you, we're trying to drive adoption. We want to see that the technology is adopted, used, and you're getting benefit out of it, because at the end of the day, it's about how good Connecticut manufacturing is. And we're trying to prove out the technologies through our lab to show you the application in demonstration form. We're validating as a neutral party that these technologies work. That's what we're here for. We'll make the mistakes. We'll break our machines, but we do it so that you see the value, and just take advantage of it while the folks are here today. Eileen will pass out the mics. If you have any questions, please get the mic.
Yeah, any questions?
How does MBD improve the efficiency of the inspection process, if it does at all? Does it help you out in the inspection process, MBD? Does it, how does that work?
Yeah, absolutely. So I skipped over a whole other subject, and we're actually going to have a future event on automated inspection. But model-based definition, particularly the QIF file, is the quality information framework. That's actually a quite a mature file format. It encodes, it holds your CAD geometry as well as your PMI and metadata. So it can actually hold like CMM points. It can hold inspection data. Like if you're actually inspecting the parts, you can encode that back in the QIF. So it's a mature file type. We use Polyworks, and we have also Geomagic here. Actually, we have a number of different inspection softwares. All of them can open up the QIF file. So if I'm receiving model-based definition, we also have PCDMIS here with the hexagon technology. We can open up that file, and it's literally a few mouse clicks. It's the same thing. You set up your strategies. Once your inspection software knows, for example, if we're doing CMM, how many points to take on a particular feature given the tolerance, it can automatically apply that strategy afterwards. If we're doing structured light non-contact, it's very easy. I mean, you're literally going at 95% efficiency, because you just open the file, import it, and it's literally 2 more mouse clicks to actually scan the part. import that into your inspection, it aligns it to the MBD file and extracts all the measured values because your tolerancing is already there. You have options for your inspection report, the output. So there's some like AS9102, PPAP, other formats that are built in that you can just call up, or you can set up a template. So you can autofill your inspection templates, or you can encode the inspection data back into your QIF and upload it through NetInspect. That's a cloud-based inspection repository. For example, I know some of the OEMs in Connecticut require their suppliers to use. I hope that answers the question. Any?
Other questions?
You pointed out on your results slide, there was a lot of data given there, but you said for accuracy, it was 86.73. What is that accuracy related to?
I was having a hard time figuring out how to present the accuracy in one number because there's a number of features that we were measuring. And so what I ended up doing was saying that out of all on the on-machine probing part, I think we had like 50, something like that, features. What percentage were in tolerance? That's what that was. So what percentage of the features were in tolerance? It's a bad number to give, but it was the only way I can get a single number in a chart as a comparison. Yep.
How does the ThirdWave software, does it feed back into the NX software in any way? Do those softwares collaborate back and forth, the data that's given there?
Yeah, so I mean, so what it's doing is when you're going to bring it from NX, let's say, into our software, into production module, it's taking the part, the tool list, and all the tool geometry and specs, and the tool path, bringing it in. We're essentially doing what we need to do for analysis, optimization. And then when we spit it back into NX, and there's an import button, and it's just one click in, it's basically taking that CL data that had modified feeds in it and just bringing it back into the toolpath that you generated within NX, and then basically puts kind of like a lock on it or a check mark. You can easily generate the toolpath, but that way it's indicated that this is a toolpath that you're essentially bringing in from a third-party software.
So what's the difference between the digital twin and machine simulation in NX itself? Is the difference only control, or it's not? Well, I'm talking about the machine-based simulation in NX.
Okay, yeah. So I'm going to say there's different levels of simulation.
Yeah.
In terms of digital twin. So the highest fidelity digital twin we have access to today is actually called NX Virtual Machine. So NX Virtual Machine resides within NX, and it uses the virtual numerical control kernel, so the VNCK, essentially inside of NX to drive the actual machine tool. So that's going to be the highest level of digital twin we have. Now, if you're just, and I can try see what Mike has to say about the basic simulation where you're just verifying the toolpath. Is that what?
No, I'm talking about the basic. I'm talking about the machine, because you can for example, you can download the machine kit from the hub, right?
Yep.
And you can simulate the machine there.
Correct. Yeah. So
it's a machine code-based simulation.
Yeah, it's a machine code-based simulation that doesn't have what we call the virtual numerical control kernel.
Yeah.
And the NCK or numerical control kernel is essentially that piece of the brain of the CNC that dictates how the machine responds. And so to put it, I guess to put it simply, the VNCK or NX virtual machine is going to be the most accurate simulation you can have.
I guess I have a part question and part comment on that because the most closely true digital twin that you can have for a TRAK SI machine is our digital twins, because our digital twins are built around our kernel and our PLC that are in the machines. So our digital twins are as faithful as you can get for our machines. So it'd be hard pressed to believe that the NX would give you a digital twin better than ours for our machines only. Is that an accurate statement?
Yes. Yeah, John. No, it's a really good point. So the NX virtual machine would still use the VCP file from your TRAK machine tool. The only difference is instead of having a CAD CAM system separate from run by virtual machine, you would have one instance of NX where you take care of your modeling, your CAM tool pathing, your simulation with that TRAK-based VCP file. If that makes.
Thank you.
Yeah, I have a question about kind of user interface, user design, UX stuff. How many years out are we from, there's like a scene in the Iron Man movie where Tony Stark is kind of pulling the holographic 3D model, and he might have an attribute like, oh, I wish it was fire engine red, you know. How many years out are we from interacting with these models in such a fluid and high bandwidth, comfortable way?
No. So the Tony Stark stuff. Sorry. So the Tony Stark stuff, not yet, but I have seen the Oculus. So doing it visually with goggles and modeling. So kindergarten version of Tony Stark stuff, like the same stuff you see in movies is what's next. But yeah, in the real world, it's expensive. That's why it's not widespread. But when we were at were you at the most recent Siemens? I forget what you were invited to and I'm invited to. But at the most recent Siemens Partner Conference, I sat in on one where they were physically doing it with the goggles, the visor glasses. So you have to be designing something high end and expensive, but it is very cool.
I'll say that on the on the inspection side, because I know for sure I'm not 100% on the manufacturing side. On the inspection side, one of the softwares we use is Polyworks, and one of the technologies out there for extended reality is what used to be the Microsoft HoloLens, but there's other ones out there now. Obviously, as time progresses, there's better and better technologies, but I know for sure that for the Microsoft HoloLens, that's extended reality means that you can see through the glasses and see your environment, but then also see like holographic projections of things in the environment. It has like a LiDAR sensor, so you have depth, to it and all that. But Polyworks had the HoloLens had like the Microsoft Store in it, and it's basically like a Windows computer on your head. And you can go into the Microsoft Store and actually install the Polyworks add-on or plugin or whatever you call it, the application for the HoloLens. And what you can do is you can actually visualize inspection data. So one demo that we actually did here was we had a turbine blade with a added weld for repair on the tip, and we were grinding that weld back down to shape. And we had the robot holding the airfoil, and we had a grinder on one side and a 3D scanner on the other side. So the robot would go up to the flexible grinding belt and actually go through the motion of grinding some of that weld down, moving it over to the scanner. It would scan it, and then you could actually visualize the deviation map so you can see where the high spots were that still needed to be put down. And we did that demo as a way to communicate to engineers that are not necessarily on site, where they can see the camera, but also the deviation mapped right on top of the physical part as it was going. So that for sure I can say because we did a demo of it. Hope that answers the question.
Is it possible to like jailbreak these machines? You know, do we have to run your software to control or manipulate the mill? And then if not, would it be in the interest of the federal government to have a different option? An open source suite of software that allows us to control your machines independent from your own software.
I can honestly say nobody's ever asked that question before. I guess I would counter and say, why would you want to jailbreak it? One, and two, the Sinumerik control is actually open architecture. There are certain, for cybersecurity purposes and also human health purposes, I'm going to say, there are certain aspects of the machine that are always going to be locked down, namely the PLC project, right? So that's created and owned, that becomes IP of the OEM who's building the machine tool. And then looking beyond that a little bit, we have a variety of what we call compile cycles. Those are also typically IP and they get locked down. But the Sinumerik control is an open architecture control. Very similarly to the NX environment, we allow machine tool builders and also users to heavily customize their machine tool equipment to, for whatever they think they need to do. But yeah, if you want to expand on the jailbreaking topic, I'd be happy to talk more about it.
Hello, fantastic demo. Love to see optimizations in productivity like that. I just wondering if the workflow is similar for CAD that has embedded parts in it and separable assemblies, or I guess the equivalent in NX would be like multi-body parts. Will like the automation know to navigate around dowel pins, alignment pins, and the like?
Yeah, I mean, generally speaking, if you have a multi-body assembly in your CAM, is this specific to CAM or design?
I guess it'll be in the CAM. The part is drafted from the multi-part assembly.
Yeah, absolutely. So in the dialogues that I brought up in the demonstration, there's an option for you to set and specifically select geometries that you want the machine to stay away from. So for example, if I have work holding device, I would choose that body as the body to stay away from. It's completely escaping me what that's called right now. But there's a specific name for it. It's there in the parameters. It's a button you click on, and then it gives you a dialogue and tells you to select the bodies that you want to disassociate with the part that you're manufacturing. That way, when you're doing the tool pathing, it'll actually, and you actually have options in the avoidance and collision detection to how you want to avoid hitting those parts. So it'll avoid the tool pathing there. But if you come across a specific area where you feel that you should have a retract, go to safe position, move over, then come back down versus go around, you have all those options available to you in the dialogue.
Siemens NX software, what do you use for encryption for your design data and modeling, 3D modeling? I think we're talking about locking down and protecting the data since it is secure. I mean, it needs to be secure, depending on what aerospace or.
That may be the the PLM system, Team Center.
So I guess I should clarify that. So you're locking down the design internally or because you want to share it? Not sure if everybody could hear you, but he's asking about sharing and storing it. And I guess my question was too basic. Is it a PDF that you're sharing now and you want to do more than that? You want to share the model itself, but still lock it down. So I don't know the answer to that question. And this time I won't throw my friend Chris under the bus, but I could find out. But I haven't actually heard that before. So, but then there's a lot of things I haven't heard before.
Sorry, this was regarding PLM.
It sounded like the NX data model, correct? So it's commonly shared as a PDF, but when it's shared as a data model, it's usually shared in full because you're sharing with a subcontractor or somebody who's making and wants to unlock it. But I haven't heard of anybody locking it. It's quite possible that it's true, and I just haven't run into it yet. So I don't want to misspeak, which is pretty much something I do all the time. So humble sales guy. I could find out, by the way, and let anybody who is interested know.
Hey, Frank, good question. So this is a little bit separate from your CAD perspective, but it just triggered something that might be interesting. So I believe in 2019, Siemens acquired a company called Identify 3D, and it just came back to mind. And what that company that company's product, what that offers is, where, for example, if you had a completed project file with the CAD data and the CAM, and you post your NC code, you can lock down this NC code and hand it to a supplier or to another company with an encryption. And so there is some end-to-end NC, I guess, protection that you can leverage, but it has nothing to do with the CAD data. But thought it might be interesting.
Sarah, you want to wrap us up?
Sure. Thank you, guys, for coming up and answering the questions. So some takeaways here. The state of Connecticut does, in my opinion, everything that it can do to help manufacturing here in the state. There's a lot of money available to you as a manufacturing company. The requirements for you to access this money are different across different programs. But one thing that I'll mention here is, we had our friends at TRAK come up first and talk about their machine tool. What you heard and what's enabled, for the price that you pay for the machine is one of the best price to performance ratios that you're going to get. So for a machine that's under $100,000, you get a Sinumerik One control, digital native control. We have a digital twin of it. We can connect edge device for very high frequency data collection. And we just demonstrated how we can take advantage of the digital thread to automatically program parts. When we take into account a packaged price, I'm going to give you a rough order of magnitude of between what you saw today, all the technologies, all the software is between $300,000 to $400,000. Okay. And that's on the high end. Depends on the options, depends on your, depends on the type of machine you want to go for. I'm going out on a limb and kind of giving you a very rough order of magnitude. The reason I'm doing that is to have, so you can see what you can get when it comes to when it comes to the grants that are available. So a lot of the software that we talked about can come under the Innovation Voucher Program, the IVP. That gets you up to $25,000. It's one-to-one cost share. You have to be a company of 100 employees or less. Oh, I'm sorry, 300, between 300 and 300 employees. And essentially, if you got a quote for $50,000, you can maximize the IVP. The IVP will get you $25,000 towards the cost of that software. Okay, so you're essentially getting half off. It's very quick application. All of these are quick applications. They're online. You spend 10 minutes. It's a digital form, and you fill it out and you submit it. You can't have committed to the technology. What that means is no purchase order should have gone out. You should be at the phase of getting a quote. You create an account on our grants page. And then you submit all the information that's required for that grant along with the quote to the digital portal, and then you'll get an application number. At that point, it takes anywhere from, depending on how many applications we have, we typically get it through in weeks, right? In a few weeks. And you could get a check cut for you for half the amount of the technology. Then you can proceed with the purchasing of it. The manufacturer voucher program is the other one I want to highlight. The TRAK machine tool, you heard, you can get systems, very capable systems for under 100,000. You can maximize the manufacturer voucher program. For that, you need to be between 3 and 100 employees. So it's targeting a smaller size company. But you right there, you get half off the TRAK machine tool. This is why I say the value is high, because for a machine that's less than 100 grand, you're getting 50% off. If you're going for you know, a higher cost machine, your return is that much smaller. So what you're getting out of what we presented today, we're trying to present to you how to maximize your you know, your dollars and your profit. There's other grants here for talent and training. We've got the apprenticeship funding program up to $15,000 wage subsidy. There's a manufacturing internship program for $14,000 wage subsidies. And for training, there's Career Connect, Rev Up, free hands-on technical training available for qualified employers. And then incumbent worker training, you get $50,000 provided annually to reimburse manufacturers for half of the training costs incurred to upskill their employees. Lifetime, you have up to $100,000 per company. So again, when I say package solution, we've demonstrated hardware that works together, edge device connected with the Sinumerik one on the TRAK machine tool. We've demonstrated the value of the digital thread and connecting all these different softwares together. Siemens, ThirdWave, Run My Virtual Machine, all work seamlessly together. And then now with the grants that the state of Connecticut affords, both in purchasing the technology, but also upskilling your workforce, right? These are all subsidized. So I hope you know, that you can take advantage today. Tech partners are here. I urge you to get quotes. We are measured as your applied R&D center, what impact we had through these demonstrations. If you're not adopting the technology, we shouldn't be looking at it. So I really urge you to talk to the tech partners, and this is a good chance to take advantage of the grants that are available. So the next Connecticut Smart workshops. This particular workshop was brought to you by this federal program called Connecticut Smart. Save the dates for now. The next one's going to be April 16th, then July 30th, then November 19th. And then in 2026, we're going to have 4 more, 1 per quarter. So just keep your eyes out. Again, we're going to keep our events page updated so you know the upcoming events. With that, I'd like to thank you for your time. We went over. Thank you for your questions. They were, we really enjoyed, you know, having the opportunity to answer them. Again, our tech partners are here. Please feel free, you know, meet them, talk about the technologies. We're gonna start the program on the machine. Come by, take a look. Again, the TRAK machine tool is very high value. It's a very good price point. You get a lot out of the machine tool, and it enables, you know, the digital thread, the digital twin. And it helps you, you know, maximize the return on your investment. Thank you so much for your time.
Is the 3 to 300 employees for the Connecticut-based division of a company? Okay. And so on the website it says the manufacturing voucher program is temporarily on hold because of funding.
Yeah, we're waiting for the funding to come from the state, but it's due to arrive in the next couple of weeks.
Okay, thank you.
So the commitment's there. We just don't have the check in our bank
Okay.
yet.
All right,
right?
thank you.
So any questions on grants, see me. I can walk you through some of those details. Michelle is also here representing our digital thread training lab. And
I'll also add that we're working closely with the NIST network of MEPs. So some of you are from other states outside of Connecticut, and there is money for you as well. So we'll make sure that no money is left on the table if you're looking towards taking further steps.
I do want to remind you, these grants are first come, first serve. Okay, so there's a bucket, you know, that the state makes available to manufacturing companies. As long as you meet the requirement, you can take from that bucket. And when that bucket gets empty, all the, you know, we have to wait for the next round if another round comes. So take advantage now while we have the funding. I just want to stress that it is first come, first serve. Thank you. We have an announcement also with TRAK. You want me to do it? They're going to have an open house on March 19, 9:30 a.m. to 5 p.m. They're going to be showing off their technologies. This is going to be at the Cromwell showroom. That's at 104 Sabbath Drive in Cromwell, Connecticut. Yep.
The Siemens team will be there, so I know today was pretty packed with a lot of information. When we did have our lunch break, we did have some questions and people wanted to investigate a little bit more. So this is just an opportunity to kind of talk a little more behind the machine, and have Siemens there to help out with some additional great questions.
Thanks, everyone. Enjoy the networking.